Hello, everyone. Good morning. And I'm a PhD student here at Carnegie Mellon, and I'm very excited to talk about blockchain address poisoning, which is one of the largest and widely targeted attacks on blockchain. Okay. So I have amazing collaborators, Mark and Kyle and Nicholas. And this paper was published at Usenix this year. Okay, let's start with some hypothetical interactions that I made up with my co-authors. I wanted to send $1,000 to my co-author Mark, and he asked me to send it to his Ethereum wallet, which is a 40-digit hexadecimal string. And I didn't want to make any mistakes, so I sent him $10 just for testing, and he confirmed. So I sent him the rest of my money. However, he told me that he hadn't received his money yet. So I double-checked my transaction, and I realized that the recipient address I specified was slightly different from his. So what exactly happened is behind the scene. I, as a victim, sent 10 USDT to my intended address, Mark's address. And after this transfer, his address shows up in my account history. So the next time I can copy and paste it, right? Very convenient. However, the attacker, Kyle, was watching this transfer and decided to generate a very similar looking address to Mark's to deceive Taro. And because blockchain wallet addresses are derived from its secret key, if he brute forces random secret keys, he'll eventually get the one that matches the first and last few characters to Mark's. And we call it a lookalike address. If he uses this address to send a small amount of money to my wallet, his address also shows up in my account history. And because two addresses are identical to each other, I might mistakenly choose the attacker's address to send the rest of my money. And as we all know, blockchain transactions are not reversible. So my money is gone with just one mistake. And the goal of our work is to identify those poisoning transfers from the attackers that try to sneak into my account history, as well as to capture the payoff transfers from the victim to the attacker to quantify overall losses. So how does our detector work? I'm going to give you a very high-level idea here. First of all, for each block, we collect a set of accounts that transfer assets, and we call it a potential victim. And then we keep track of each potential victim for the next 100 blocks, assuming that attack potentially happens right after the original transfer. And then we calculate the similarity of newly interacted address based on so the distance metrics we use is simply the number of consecutive matched digits in the beginning and the end until the different character shows up. So in this case, it matches the first 6 and last 4 characters, and we only consider it to be lookalike if the score is more than 3 and 4 to avoid natural collision. And finally, we check whether the victim makes mistake and transfer assets to the attacker. And we show that this detector is actually pretty accurate. One of the validations we have done is to use the external data set to identify lookalike addresses from the pool of benign addresses, and we achieved 100% precision and 97% recall. And we ran this method for 2 years of Ethereum and Binance Smart Chain after the fact. And we identified 270 million attack attempts, poisoning transfers, over 70 million victims, and 6,000 cases contributed to $84 million losses. And just to give you a sense of how active the attackers are, on the most active day, on BSC, we see 35 attacks every second. That means the resources wasted on poisoning transfers are not negligible. In addition, we observed many more attacks on BSC, probably because the transaction fees are much cheaper. But in terms of losses, it is significantly higher on Ethereum because the average transfer size is generally larger. So this means that the blockchain with smaller transaction fees, but with many more economic activities, is most vulnerable to this kind of attack. And finally, because wallet addresses are compatible between those two chains, we observed 17,000 lookalike addresses that are reused between those two chains. And this means that the attack is easily scalable and generalizable across chains. So at this point, our question became, who is actually behind this attack? So we started to merge poisoning transfers to form attack groups. And we are not only looking at lookalike addresses, but also any kind of addresses that support these poisoning transfers. And we merge two poisoning transfers in the following way. The first case is when they are launched in the same transaction. Oftentimes, attackers bundle many transfers in one transaction to save a transaction fee. So if they are in the same transaction, they belong to the same guy. The second case is when they use the same transaction address, the same address to pay transaction fees. This is simply to assume that attackers do not share private keys. And finally, if they use the same lookalike addresses. In the end, they have to extract money from the lookalike addresses to get the assets. So there's no economic incentives to specify other people's lookalike addresses. So we ran this clustering, and we established 49 groups in total. And we assign group IDs based on the number of lookalike addresses they have. And this table shows that the attack is very large scale, right? So the top three groups employed more than 1 million lookalike addresses and performed millions of transfers that cost millions of US dollars. So our question is this actually profitable? The quick answer is yes. But we wanted to know who is actually profiting the most. So we looked at the cost and revenue. So in this figure, x-axis is the total cost, which is the sum of transaction fees for poisoning transfers plus the value transfer to the victim. And y-axis is the sum of payoff transfers. And each data point represents one attack group, and the number is the ranking by size. And you can see that the group one actually invested a few million US dollars just for poisoning transfers. And in general, large groups are highly profitable. They experienced about 10 to 20 times the return of the investment, whereas they dominantly win against smaller groups. And the reason is that the variance of the payoff transfer is quite high. So if you're lucky, you get millions of dollars at once, but most of the case, you just get $100. And we actually show that there is another advantage of large-scale operation. So when we are looking at successful cases, we realize that 79% of the time, multiple attackers are targeting the same victim. So we can actually see that who is actually win the game for each victim. And this figure shows the winning ratio for the groups in y-axis over the groups in x-axis. So for example, group 2 wins group against group 8 92% of the time, so we have a darker blue here. So it shows that the large groups are very competitive. So the winning ratio stays around 50% of the time, whereas they dominantly win against smaller groups. So, and we have another experiment to show that the reason why. Because the larger groups have more resources to conduct attack early or generate more similar looking addresses. So we actually looked at the similarity score distribution of those lookalike addresses. So in this figure, x-axis is the number of total match digits in the beginning and the end. And y-axis is the number of lookalike addresses generated by each attack group. And you can clearly see that group 1 managed to generate much more similar looking addresses than other groups. And where does the difference come from? So we mathematically approximate how many attempts actually you need to generate such an address. And it is about 16 to the power number of matched digits divided by the number of target addresses. So for instance, if we want to match 7 addresses, 7 digits, and OK to be matched with any of the 100 accounts you're targeting, you need 2.7 million attack attempts. And then we empirically estimate how many addresses you can actually generate per second so that we can approximate how long it takes to generate a lookalike address. So we started with the off-the-shelf implementation using Python and Web3, and we can generate up to about like 1,000 addresses per second. Then if we optimize the type of libraries and programming languages, we can achieve up to 10,000 addresses per second. Then if we add GPU on the top, we actually see the leap in the performance. The attackers can generate about 1 billion addresses per second, which is very frightening. And if you remember the figure from the previous slide, the group 1 managed to generate 6 more digits than other groups, which requires about 10 million computational power than other groups have. So this means that group 1 must have used GPUs or any kind of like specialized machines to generate such a lookalike address, because generating that by CPU takes astronomical number of years. And so how can we mitigate this issue? Like I'm going to touch briefly. I'm going to talk about only a few of them. So at the protocol level, we can make it difficult to generate a lookalike address by adding latency for the address generation process. And at the wallet level, the providers can implement heuristics to give a warning when a user was about to interact with a lookalike address. But in the end, this comes to the user's mistake, right? So it is really important to warn users of the severity of this attack. So as a follow-up of this study, we actually developed a real-time detection system called Toxin Tagger that can actually keep up with the speed of the chain. And I would like to show you the website. So if you have a phone, please scan this QR code so that we can walk through together. Or you can type this URL as well. And by the way, the second author, Mark, led this implementation, and great job. So, and he's actually the speaker of the next talk. All right, so in this website, we broadcast whenever someone makes a mistake. And if you click one of the cells, you can see that exactly when the victim makes initiates the first transfer and gets attacked by the attacker, and the second row here, and makes the mistakes in the end. And someone lost $12,000 about a week ago. And we also have social media account that broadcasts on live. So if you like this system, please follow us. That would be a great help. OK, to sum up this talk, we identified 270 million attack attempts and also 84 million US dollar losses, which makes address poisoning, again, one of the largest and widely targeted attacks on chain. And we show that there exists an economy with scale. And large groups are profitable and dominating the market. And I find it really interesting that based on measurements, and only based on measurements and simulation, we can infer that the attackers are hardware types. And we disclosed findings to the wallet providers and made data set publicly available. So, and I couldn't talk about a lot of experiments in my paper. So if you're interested, please reach out and scan those QR codes. Thanks for listening.
Okay, we have plenty of time. About 5 minutes for questions. Yeah, let's go. Can you show us the profitability slide about the cost and revenue? So when you say the cost, like you later talk about the use of GPUs, and thank you. I guess maybe you should include those hardware and electricity costs into the total cost as well and reanalyze the profitability.
Yes, you are right. In this figure, it doesn't include the computational cost. But in our paper, we analyzed how expensive it is to generate by CPU. And in general, CPU and GPUs generate very expensive. And the cost is not negligible, but they are still profitable, even if you incorporate the computational costs. In CPU, it's very negligible. So it doesn't really affect here.
Okay, it would be great to see the picture with the GPU considered, but I guess I can find it in your paper.
Yes, and only group 1 appears to use GPUs.
Okay.
Yeah.
Thank you.
Yeah, so if an attacker want to carry out this kind of attack, they need to send a small amount of money to the victim's wallet, right? And I was wondering if it's possible to attract this kind of attack to profit from it. Like, you got to send me a small amount of money. Is it possible for me as a victim to create a bunch of wallet to attract this kind of attack to profit?
Generally, you can. So theoretically, yes. But the transaction costs, if you want to attract attackers, you have to keep transferring assets between accounts. And usually the cost of transaction is much higher than the amount you're receiving. Because usually the amount of money you get is like 1 cent.
I see, thanks.
Yep.
Just a very quick question. What's your policy recommendation, or what should people do?
So I think the best practice is to whitelist on the intended address. Also, are you asking about the recommendation for individual or the provider?
Well, yeah, you're identifying an issue that could affect people that transact on these networks. So then the question is, how do you protect people from this?
So I think one of our contribution is to warn that there is a lot of activities going on social media. But in the end, it comes to as you said, individual users. So when you try to specify the address, probably you shouldn't copy and paste every time, and just to check every digits, or as I said, whitelist your intended address.
Okay, great. I think, let's thank Taro one more time, and